Boa noite a todos. É com grande satisfação que estou aqui hoje para introduzir o professor Jorge Macedo na apresentação dele sobre a análise baseada em estado na manifestação de liquefação cíclica. Gostaria de começar agradecendo muito o Geotecnia Brasil pelo convite, agradecer também o professor Jorge Macedo por dispor do tempo para fazer a sua apresentação e principalmente a todos vocês que estão nos ouvindo. Eu vou fazer uma breve introdução dele em português, depois vou passar a palavra ao professor, ele vai fazer a apresentação dele toda em inglês. Ao final, a gente vai abrir as dúvidas. Pessoal, vocês podem mandar aqui no chat, nos comentários para a gente, que a gente vai fazer as perguntas para o professor. Vamos tentar fazer uma ajuda também aí, eventualmente, algum detalhe de tradução para poder finalizar. Então, sem mais, o professor Jorge Macedo, ele é PhD, ele também é um consultor e um professor associado da Escola de Engenharia Civil e Ambiental no Instituto de Tecnologia da Geórgia, no qual ele se juntou como professor em 2018. O Dr. Macedo, ele também pratica a engenharia geotécnica há mais de 17 anos, trabalhando como consultor em grandes projetos de mineração no Peru, na Argentina, no Chile e no Brasil, desde os estágios de concepção até os estágios de detalhamento de projeto executivo em engenharia detalhada. E ele mantém um título de engenheiro profissional, Professional Engineer, o certificado, tanto na Califórnia quanto no Peru. A principal área de pesquisa do Dr. Macedo são engenharia geotécnica aplicada à mineração, engenharia sísmica de terremotos e a análise de múltiplos riscos, engenharia aplicada de múltiplos riscos, baseada em dados. Ele recebeu o prêmio em 2022 nos Estados Unidos da Fundação Career, do Serviço da Agência Nacional de Ciências dos Estados Unidos, pelo seu trabalho em ciência de dados e engenharia com rejeitos e convergência de rejeitos geotécnicos. Mais recentemente, ele também recebeu o prêmio de jovem pesquisador da Associação Internacional de Mecânica dos Solos e Engenharia Geotécnica, a ISSMGE, e vários prêmios de pesquisa educacional no Instituto de Pesquisa na Geórgia. O Dr. Macedo, ele é o fundador e presidente do TAILENG, que é o Tailings and Industrial Waste Engineering, o centro de pesquisa que trabalha para melhorar a resiliência da infraestrutura nas indústrias de mineração e de energia. Então, sem mais delongas, vou passar a palavra ao professor Dr. Macedo.
Perfect. Thank you, Diego. Thank you very much for the kind words. I understand Portuguese, but I cannot speak Portuguese, so I apologize for that. But I'm a Spanish native speaker, so I kind of I pick up. So, but maybe the questions are going to be better on English if the audience doesn't mind. So I will go ahead and share my screen and get started with the presentation. Give me a second. Okay, so I think you should be seeing my screen right now. Can you please confirm that that you can see my screen? I know, Diego, could you confirm that you can see my screen? Good.
Yes, we can.
Okay, perfect. Thank you very much. So I wanna thank Felipe Cruz and the geotechnical community in Brazil for this invitation. It's really an honor to be here and speaking to the community in Brazil. I was in Brazil several times. Initially, it was for work, and one of the last travels on May, it was because of a short course that we were offering, and I had, I would say, the chance to really interact with a lot of Brazilian engineers, which was really, really amazing. I really enjoyed that experience. It was back on May. So again, I want to extend my gratitude for this invitation. So I'm going to be talking about state-based assessment of cyclic liquefaction manifestation, and one of the motivations for giving you this talk today is kind of related to the unique materials that you may find in Brazil. At least that has been my impression, and that is also the case for the mining industry, where you have also, for example, mine tailings that can be quite particular. So in this talk, I'm going to be hopefully providing you kind of an alternative view on how to assess the manifestation of cyclic liquefaction. And I'm going to be walking you through the different, steps. The outline of this talk is as indicated on this slide. I will start with the background and motivation, and also give me a second just to check the time and make sure I'm going to be within the time constraints we have. So as I said, I will start with the background and motivation, and then I will move into talking about the traditional cyclic liquefaction assessment, so how that is done, traditionally. And then I will be offering you an alternative that is a mechanistic-based procedure for cyclic liquefaction assessment, an alternative that we believe has potential, and I'm going to be saying more words about that. And I will be closing just to show you a case history, an application of the approach into a case history. The materials that you are going to be seeing today are published in a couple of journal papers. We published on the Soil Dynamics and Earthquake Engineering Journal. So if you're interested, you can go there, or please feel free to email me or email, I guess, Felipe, if you don't have my email, and I'll be more than happy to provide the papers. So, okay, let's just start with the motivation and with some of the challenges. So, one, initial challenge is that nowadays, 2024, in the state of practice, the procedures for evaluating static and cyclic liquefaction are contrasting. They are not consistent. So, for example, in Brazil, you had significant failures of tailings storage facilities like Brumadinho, Fundão, and typically those have been associated with static liquefaction, and there is kind of a set of procedures that is used on static liquefaction. On the other side, on cyclic liquefaction, the procedures are mainly empirical so far. On static are informed by mechanics, in my opinion. So there is kind of a contrast in terms of how the different assessments are conducted. So that's one initial challenge. Second challenge is that there is a limited case histories for intermediate materials. With intermediate materials, I'm talking about, for example, mine tailings or silts. I'm gonna be showing you some figures later that are kind of making a case for that. So in that context, there is also uncertainty in applying traditional approaches that have been developed for natural soils. In most cases are sands and silty sands, to intermediate fine-grained soils or waste materials, for example, mine tailings. What I'm trying to tell you here is that most approaches for cyclic liquefaction have been formulated for clean sands or sands with some fine contents, and the application of those approaches to other scenarios for which have not been explicitly calibrated for needs to be thought of or considered carefully. For example, in the case of mine tailings, you have this is a database we created for mine tailings, This is published on the Canadian Geotechnical Journal as in one of our recent papers, also on the ASCE as Vergaray et al. This was a work with my former student, Dr. Luis Vergaray. So, and we had kind of different set of information. This is just showing you the amount of fine contents, and the particle size distributions. And as you can see, most materials are actually fine-grained materials. So this is just to make the case that, as I'm going to be showing you in later slides, the traditional approaches have not been really formulated for materials like that. So now, let me here just show you what is the traditional approach. So the traditional approach is, please pay attention to this chart over here, and hopefully you can see my mouse. It's an empirical approach where engineers were going to the field after an event, after an earthquake, and there was a documentation of liquefaction manifestation. If liquefaction was observed in the field, typically through ejecta, so if there is kind of a manifestation of the material that was, beneath the surface, going out to the surface, that was classified as liquefaction, and those are the red points over here. And on the opposite case, where there was no manifestation, it was characterized as no liquefaction, which are kind of the white circles over here. Now, the y-axis over here is the seismic demand. So this is CSR. It stands for cyclic stress ratio. But you can think of this as the equation is over here, as you can see. You can think of that being directly related to PGA. So, and also is going to be scaled by the level of total stresses and effective stresses. And RD is going to be just a depth scaling factor that is accounting for flexibility. Okay, so bottom line, y-axis is telling you the demand. And the x-axis is kind of telling you the resistance. So how resistant is your material? In that particular case, I'm showing you as a normalized tip resistance corrected by fine contents from Boulanger and Idris. So, and the idea is that if you have, cases with liquefaction manifestation and cases where you don't have, well, you can draw a curve over here that is going to be separating them. And then you can define a safety factor where the numerator is going to be your resistance. In other words, the x-axis over here, and the denominator is going to be your demand. In other words, the y-axis over here. If your resistance is higher than the demand, well, you're good. You're going to be on that side of that chart, and that means that there is no liquefaction manifestation. On the other hand, if the opposite is happening, you will be on that part, and you have liquefaction manifestation. Now, based on this safety factor, researchers were calculating liquefaction severity indexes, which is nothing but, a convolution or a combination of the different safety factors that you have at different depths. There are different formulations for that, but the idea is pretty much that. It's not changing. So now, this is the traditional approach, as I mentioned, and what I'm showing you here on the bottom figure, so is different information, and let me walk you through that. For example, here, I'm showing you the depth of the critical layer or zone on the y-axis, and the x-axis is the fine contents. The first thing that I want to bring to your attention is that most data over here is, having a fine contents that is below 30%. And limited data here is having a fine contents that is higher than, this is about 30-something%. And even if we go to higher fine contents, let's say 75%, it's going to be even, more limited data. So we don't have really, much data on the traditional approaches on those regions over here. Similarly, if you look at I sub C, this is the soil behavior index from the CPT. Most data is having an I sub C that is lower than 2.5, as you can see here. Only scarce data is having an I sub C that is higher than 2.5. And remember that as a rule of thumb, an I sub C of 2.6 is typically, used to differentiate behaviors from a sand type to a clay type. So this is another, example of the limitation of the data used to formulate the traditional approaches. And by the way, I'm using this based on I'm kind of stating the example based on the Boulanger and Idris 2016 publication. And then in terms of effective stresses, so you're seeing the data over here, most of what we have out there is for stresses lower than 100 kPas, as you can see here. So for anything that is higher, we also have kind of a gap over there. So the point here is that philosophically, this approach is empirical. So as such, it's going to be working fine for cases, or for observations you have within the data set. But for cases that are outside the data set, you cannot really assure that's going to be working fine, because it's now an extrapolation and there is no data there and the approach is empirical. So now, in terms of the liquefaction severity indexes, as I mentioned over here, I did show 3 examples. And this is how they are typically calculated. The liquefaction severity index is going to be a combination of the safety factor and a weighting function. And the weighting function is changing with depth. So, for example, when LPI is the liquefaction potential index. When it is used, F, this function over here, is going to be nothing but 1 minus the safety factor. And the weighting function is going to be as 10 minus 0.5 Z, where Z is depth. So similar to LPI, on LPI-ish, which is a relatively newer, you have just a different function for F. And then when you go to LSM, you will be having a different function for F. In that case, this is the volumetric strain. So the concept, as I mentioned, is that you are combining safety factors with a weighting function. That's all that's happening. So now, I'm showing you here a bit more data to keep making the case of the limitations on the empirical approaches. Here I'm just showing you the same figure as it was before, but now I'm showing you some histograms. And take a look to the histograms for the large fine contents over here. It's significantly, scarce cases compared to lower fine contents. Likewise, when you're looking into I sub C, you see only a handful of cases for I sub C values that are higher than 2.6, and the same for stresses. So same message as in the previous slide. I'm just showing you the distribution with histograms over here. Now, one approach that we put forward in the papers that I was mentioning, and I'm going to be showing you some of the details in the next slides, is to use a state-based approach. In that state-based approach, the demand, CSR, remember this is just representing the demand, is the cyclic stress ratio. This is not changing. It's exactly the same, as you can see. It's just scaling up PGA, total stresses, effective stresses, and also the RD factor. Now, what we are changing is how to estimate CRR. And the case that we are making is CRR can be estimated based on the state parameter. So, and the state parameter, can be estimated from mechanistic properties. Like, for example, here I'm showing you the normalized Q, that will be the normalized tip resistance, the normalized BQ, that will be the normalized pore pressure from the CPT, Gmax, that's just the maximum shear modulus that is calculated also from if you are doing a seismic CPT, you can get that from the seismic CPT. MTC is just the critical state stress ratio. N is a volumetric coupling, and you can get that from triaxial tests, for instance. Chi is just the state dilatancy scaling. You can get that also from triaxial testing. And then upper gamma and lambda are the slope and the altitude of the critical state line, and P is just confined. I'll be talking a little bit more about all of this, all of that information. But the idea here is that you can estimate CRR from a state. And you're going to be finding 2 families of methods. Direct methods, for example, the procedure of Robertson 2010, where you can estimate CRR directly from CPT data, or you are going to be finding like the Pewell's procedure, same idea, you estimate CRR from CPT data, or the Bing and Jeffries procedure, where you also estimate CRR from CPT data. Now, there are other also alternatives for estimating, the state parameter, and it's the cavity expansion and also finite element modeling, and you have a different contributions that are directed towards that alternative. At the end of the day, the estimation of the state parameter is posed as an inverse problem. An inverse problem meaning that you go to the field and what you measure is with a CPT is going to be the tip resistance and other measurements in the CPT, and what you want to really know is the state parameter. It's pretty much how you invert the measurement from the CPT into a state parameter. So anyways, once the CRR is calculated, now you can proceed as usual and calculate your safety factor, and you can calculate your severity indexes as well. Okay. So now some clarifications here is that on this approach, this is not limited to fine contents and stress level, assuming that we don't have crushing, because we are capturing the mechanistic aspects of the response through the mechanistic parameters that we are using. The extrapolation is expected to be more robust because, again, we are relying on mechanics. It's not just empirical. And then, it can be also, you can have regional versions of the procedure as far as you have data. I will be showing that a little bit more in the next slides. So now, one of the key aspects of what I have been talking about is the CPT inversion. That means that you go to the field with your CPT, and as I mentioned, you measure, the slip friction, you measure pore pressures, and you measure tip resistance. But from these measurements, you want to know really a state. You want to figure out what is the state parameter. So there are different ways of doing that. For example, you can do cavity expansion. Many of you may have used the Whittier that is quite popular in practice, especially for those that are doing a static liquefaction for estimating what is the state from the Whittier. And the equation is just this one over here. But typically, when you are using the Whittier, you need to scale up the normalized tip resistance that you get from the cavity expansion, because a cavity expansion is not compenetration. It's a proxy to it, but it's not that. And then those factors that are used in the inversion can be related to mechanical properties. So that's the overall idea over here. Now, in terms of inversion procedures, we document them in our paper. So I suggest you to take a look to our paper if you want to see the details. But typically, they are going to be having these forms. For example, this one over here is the form for Pewell's, Bing and Jeffries, and Robertson. And we have some alternative forms. In our paper, we also discuss that the Robertson procedure can be also showcased as an inversion problem. So where now the K and M are kind of given by these equations over here. Now, let's talk about the mechanical parameters now, because so far I'm telling you that we are going to be doing a CPT, and we need to back calculate the state from the CPT. For that, we need to have mechanical properties. And those mechanical properties are, common, I would say, for static liquefaction assessments. And what we are kind of, the case that we are making here is that we can use them for cyclic liquefaction now. So, for example, the critical state line, you do a set of triaxial tests, and then you evaluate what is the final or the ending condition that is representative of a critical state condition, and you can get a critical state out of it. And typically, you can have a linear or a curve relationship that's more a flavor rather than something really very relevant, I would argue. It depends on the level of stresses you are dealing with, of course. And there are fundamental aspects on why you're getting curvature, but that's a different discussion. So then you have the stress ratio, the critical state, which is nothing but what would be the stress ratio when you are getting to the critical state condition, as the name suggests. You have the state dilatancy parameter, which is just scaling, the state with the maximum dilatancy. remember that if a soil is having a more negative state, you are going to be having a dilation that is higher. The mean subscript over here is just to is pretty much because of the convention on soil mechanics that expansion is negative, and because of that the dilation is negative. So, and then you have also stiffness related properties where you have, for example, the shear modulus being related to the confinement through different functions. All of these parameters, or most of them, can be calculated from triaxial testing, as you can see here. For example, this is the void ratio and the confinement. This is the maximum stress ratio and the maximum dilatancy. Each point here is just a triaxial test, and you are just picking up the points with maximum dilatancy and maximum stress ratio. Then this chart over here is just showing, the maximum dilatancy and what is the state at that maximum dilatancy. So each point over here is also a triaxial test. And then if you add Bender elements to your triaxial test, you can get a relationship between the maximum shear modulus and the confinement. Or, alternatively, you can also do your physical tests, for example. So now, so far I have given you the ingredients that we are going to be using, okay? We're going to be using CPT to estimate the state, and to estimate the state, we're going to be requiring of mechanical properties. Now, we need to have a framework to evaluate how good our different models are, performing. So that can be done using machine learning, and this is what we did. So there is a technique on machine learning that is known as the receiving operating characteristic curve. And the idea is that, let's say that you have these two distributions over here, and then there is going to be a threshold pretty much to separate the data that is actually on one category, where a category can be, if liquefaction has been manifested or not, from another category where this other category can be that liquefaction has not manifested. And then, for that threshold, for instance, you are going to be having some cases that are true positives over here. In other words, cases that where you saw liquefaction and the method is actually classifying that as liquefaction. But you're going to be having cases where, those are going to be false positives, meaning that they are actually on that distribution here, but your threshold is classifying that as I would say, not in the correct category. So you will have true positives, false negatives, and true negatives. And then if you define the true positive rate and the false positive rate, a figure like that can be created where the y-axis is the TPR and the x-axis is the FPR. And if you plot the data over here, the closest this curve is to the upper left part. So here, the better your classification, threshold is working. So, for example, this if your classification is separating, two classes like what I'm showing over here, hopefully you can see my mouse, that will be a pretty good, separation, because we are not seeing almost overlap between them, and this curve is going pretty much to the upper left. Now, if it is doing kind of an okay-ish work, it's going to be looking like that, and the curve is going to be moving on that direction. And if it is not able to really separate the cases, the distributions are going to be looking pretty much the same, and this curve is going to be looking like a linear one-to-one line over here, okay? So now what we have done in that sense is to evaluate the framework that I have described using the Canterbury earthquake data. So let me give you a little bit background on that. During 2010 and 2012 on New Zealand, on Christchurch, there were kind of a sequence of earthquakes that were occurring. And that was quite interesting and quite unusual, because you were having a bunch of earthquakes within a relatively short period of time. And then, on New Zealand, that caused significant liquefaction damage. So, and because of that, and other aspects as well that I don't have the time to dive in, there were a lot of seismic, and not only seismic, but CPT investigations as well. indeed, what you are seeing here on that map, each dot here is a CPT. So you can see that there is a lot of data here. So in order to evaluate the framework that I was describing, we did go to that database and we look at every single CPT over there, and we decided which ones we're going to be using forward for the assessments that I'm going to be showing. So and we did that based on a database that is available for the Canterbury earthquake sequence. And also we calculated the demand based on the PGAs that were observed during the earthquakes. So now on step number 2, we are calculating what is the state. And for that, we are calculating the state from the CPT data. And then we are using direct methods, meaning that this is just an equation to calculate the state from CPT data, very simple to be applied. Or we are using cavity expansion-based procedures, where K and M here have been calibrated based on cavity expansion simulations. And then within this category, we realize, as I'm going to be showing you later, that the existing procedures, based on cavity expansion, were not working really well for New Zealand. So we formulated and provided a new procedure as well. So now the other ingredient that we need is kind of a liquefaction resistance curve, where the liquefaction cases are separated from the no-liquefaction cases. So we look into a curve that was recommended by Jeffries and Bing, and was that in turn was based on some case histories from Moss 2003, and this is the curve that we decided to use. Now, what we did is for each site we calculated the safety factor profile, and then we calculated the liquefaction severity indexes as well. Which again, remember that is just a combination of the safety factor profile with different weighting factors. And we did that for all CPTs that you can see that I was showing on the previous figure. And in that step, we calculated LPI, LPI-ish, and LSN indexes. And then we were getting kind of distributions. And for example, in the database, we have also a tag that is telling us for a given case if there was liquefaction or if there was not liquefaction. So now we have distributions like this one. The yellow is no liquefaction and the blue one is liquefaction. And we are going to be using kind of different thresholds to try to separate them. And for each one of these thresholds, for example, if the threshold would be A over here, we will be getting a value on that curve. If for another threshold we'll be getting another value, for another threshold we'll get another value, and in that way we can build that receiving operating curve. Okay, and then for the different models we will be having different receiving operating curves, and the better models, or the models that we are kind of ranking as better, they are going to be moving on that direction. And the opposite is going to be happening for the other models. So now let me show you some of the results. And remember that we are using kind of a variety of procedures. And just to remind you about that, and let me highlight this again. Remember, direct methods, we have this, and cavity expansion ones, we have these ones over here. So now, in terms of direct methods, they were working. Oh, by the way, I am also showing the Boulanger and Idris 2016 procedure over here, which was used in New Zealand extensively. And I'm showing you over here the direct methods. Those methods are just estimating a state from the CPT directly, and then we're using a state to estimate CRR. Remember that, okay? So the performance is quite, I would say, similar in all cases. LPI, LPI-ish, and LSN are just working fine from that perspective, because the curve is relatively close to the upper, left range over here. And now when we looked into the cavity expansion-based procedures, now we started to see some differences. For example, here, and again, the Boulanger and Idris and the Robertson 2010 procedures are shown over here. Those are kind of traditional procedures which are expected to work properly, because those have been calibrated with case histories in New Zealand. In the other cases, the purple curve over here and this one over here are cavity expansion based approaches, and then the red curve over here, that one is a curve based on finite elements. Okay, so something I should have added over here is that it's not only cavity expansion. Also, we have a curve that is based on on finite element simulations. So, but the takeaway from these plots over here, remember the better performance is when these curves are going to the upper left. So the takeaway is that the cavity expansion procedures are having, I would say, in terms of performance, the performance is not as good as the others, as you can see, because those are closer to the diagonal. And in particular, this procedure, this curve over here, which is from Shadon and Jeffries, was not really performing good on New Zealand. So now, what we did as the next step is, given that these cavity expansion-based procedures were not working well, what we did is, let's calibrate actually a set of factors that are going to be updating those cavity expansion-based procedures that are out there. And one of the motivations for that is because cavity expansion procedures are quite, popular in practice. So we wanted to update that. And this chart over here is kind of showing, the procedure that we follow. So we start with a database, and then we get, the magnitude and the PGA out of the database. And, we, for example, we are using the Boulanger and Idris procedure in terms of the traditional approaches. And then we were getting the CSR, the CRR, safety factor, and the liquefaction severity indexes, as I mentioned, and calculating the receiving operating curves. Now, we did the same with the Robertson procedure. And then, we also looked into the, I would say, state-based procedures that we are putting forward. And for one of them, that is the cavity expansion, what we did is we try out different C1 and C2 values. And remember, C1 and C2 are the constants that are mapping the state parameter that you are getting from cavity expansion into what's going to be a field-based state parameter. So what we did is we conducted a sensitivity study, changing those C2 and C2 values to different realizations to create a map that's going to be looking like that. So, and we created maps for different, liquefaction severity indexes, starting on LPI, moving into LPI-ish, and then going into LSN. And what you are seeing here, x-axis is C1, and the y-axis is C2. And remember that those factors, C1 and C2, are used to scale the, the property or the factoring parameter that you get from the cavity expansion simulations into field values. Something else that you are seeing over here is kind of the sensitivity of different combinations of C1 and C2. For example, the top figure over here is showing a C1 of 0.1, and how the different cases are changing when you increase the C1 for a constant C2 value over here. And the different histograms are just showing, how good the calibrated parameters can be separating liquefaction from non-liquefaction. So we repeated that many times, and we created those contours over here. And then what you are seeing here as colors is the area under the curve, which is nothing but the area that you have, if I go back here, is the area under those curves. So if those curves are closer to the upper left part, the area will be higher, and the method will be performing better. So what we are going after here is pretty much the curves with the highest values here. And in that particular case, we were finding that this combination was actually providing us a high AUC value, and at the same token, it was giving us an LPI value that is consistent. Here, for example, we are in the range between 5 and 15. It's consistent with values that have been observed experimentally, or sorry, on the field, which is good. So we did the same for the other cases, and in that manner we constrain, our C1 and our C2 values. And now, for those constrained values, what we did is to repeat the procedure and then to calculate the receiving operating curves. And I'm showing you here, the final result. So, for example, the three existing procedures based on cavity expansion are shown over here, where this line here is the Sutherland-Jeffries procedure. This one over here is Jeffries and sorry. This one over here is the Jeffries and Sutherland 2016. This one over here is the Sutherland-Jeffries 98, and this one over here is the Gafasi and Sutherland procedures. And then on green is our updated procedure, where you can see that this curve has moved to the, I would say, to the upper left, on the upper left direction, which is good. That's what we are kind of going after. And then, we compared over here how our updated, inversion procedure, or cavity expansion-based inversion procedure, was working in the context of the Boulanger and Idris 2016 and the Robertson 2010 procedure, which have been formulated for natural soils. I have to, highlight that. And I'm showing you also, this procedure here that is based on finite element simulations as well. That the reason why we're showing that procedure here is because when you have a cone kind of penetrating, cavity expansion is going to be only a proxy for the penetration. If you're doing finite elements, that's going to be a better proxy. Of course, it is still having limitations as well. So the takeaway from this is that the proposed framework, is as robust as the Boulanger and Idris procedure for New Zealand. However, the mechanistic framework can be extrapolated to different conditions than we believe that the Boulanger and Idris procedure have not been formulated for. For example, cases that are outside the database, and that would be applying to any empirical procedure in general, because an empirical procedure is based on the data for which it has been created. So on the next slides, I'm going to be showing you also an application of this procedure for a case history. Okay. So before I go into that, here is a comparison of different metrics. The AUC is the area under the curve. Remember, the highest that value, the better the procedure. And the OOP is going to be the optimal value for separating liquefaction from non-liquefaction cases. And then what you are seeing here on each row over here, these are the two first rows over here are the empirical-based procedures. This is kind of a state of practice. Then you have the Bingham and Jeffries 92, the Peebles procedure, and the Sutherland Jeffries procedure. Those procedures are based on either direct equations or cavity expansion. And then we have a cavity expansion, updated procedure over here. So, but I want to bring to your attention also that, for example, the Bingham Jeffries and the Peebles procedure were providing OOP values that were quite low. That means that the separation between liquefaction or non-liquefaction is going to be affected just by a small variation of what is, for example, on this case, LPI. And you don't want that. You want a method that can be actually have some sensitivity to separate cases. So in that context, we in the paper, and in the case of New Zealand, we were not recommending, those procedures over here. So we were favoring, either the procedure based on finite elements or the procedure we recommended to be used, which is a calibrated cavity expansion. And of course, the empirical procedures are working also fine on New Zealand, because to some extent, they have been calibrated with significant data from New Zealand. So, and the same history applies for the other, liquefaction severity indexes. So, but now, again, the other takeaway over here is that the difference philosophically and conceptually is that, the procedures that we are trying to put forward, or the framework we're trying to put forward, is relying on mechanistic properties. And now, when we did the evaluation for New Zealand, we were kind of estimating those mechanistic properties from the CPT. So we were not doing really anything that was more complex for fixing or constraining those properties. In other words, you can use it right away, right now. If you have a CPT, you can use the procedures that we have been discussing on this paper. So with the, I would say, with the added value that you could actually use the procedure for a site-specific case study. For instance, if you have a tailings dam where you are assessing cyclic liquefaction and you have already done the testing for static liquefaction assessment, you can use that information for the assessment of your particular facility without relying, to a procedure that has been formulated in a general way using data from many, many locations. Now, we apply the procedure to a case history that happened on, that was on California, and it was the Harbor Bay Business Park liquefaction case history. And this is a very nice case history. It is published on one of our journal papers. And I'm saying that it is nice because we had CPT data before the earthquake and also after the earthquake. And we have CPT data since approximately 1984. And then CPT data has been collected kind of periodically over there. So we have data from 1984 to about 2019. So that is about more than 30 years of data approximately, if I'm making the math correctly. So we did look into all of the data, and we learned a lot of things. For example, how the earthquake is changing actually the density of the materials that you have there, and many other things. So just to give you a general idea of the stratigraphy on that site, the CPT resistance or the CPT traces are looking like that. This is the tip resistance, this is the pore pressure, this is the normalized pore pressure, this is the frictionless lift ratio, and this is the undrained strength. So as you can see, there is a dense sand field over here, which is followed by a loose sand field and interbedded silty sand, and also interbedded sand clay mix over here. You have a Holocene bay mat over here. There is the Merritt sand here. There is a dilative Pleistocene bay mat that is showing up over here with some variations. So in general, we focus on these two units for our assessments. So, and here I'm showing you a little bit of the, of the comparisons of CPT responses before and after the Loma Prieta earthquake. The Loma Prieta earthquake happened in 1989, and as you can see here, it seems that there was a movement from left to right for that particular, material that was the loose sand field over here. Meaning that after the earthquake, the tip resistance, it seems that it was kind of changing by that amount over here. But now, but that, is not really a general statement, because on some other cases, we were seeing kind of more different variations. So it's really a complex problem to see how the resistance of a particular soil profile is changing before and after the earthquake. So we had also, evidence of ejecta over there, so that we use for our interpretations. And something that we did is to conduct triaxial testing with samples that were recovered from the site. This is the HBBP sample. And with that triaxial testing, we calculated our properties, for example, the critical state line, or the state dilatancy parameter, or the N, the volumetric coupling. And we use all of that. And one of the things that we did was to also update on that, to calibrate the Pewell's procedure, the Pewell's inversion procedure for our site, because the Pewell's procedure, when you have a normalized friction ratio that is kind of low, it tends to give values that are high for the CPT inversion K coefficient. So based on our triaxial test and the calibration of K and M, using cavity expansion, we kind of modify this, this trend over here, and we propose the green trend over there. And then we use that also to have an approximate transition from drain to drain behavior. And that was informed by the cavity expansion simulations that were conducted over here. So, and here you can see these are CPT charts over here, where you can see the different variation for different units, going from the dense material that is kind of on the top to other variations over here that are showing, for example, silt-contaminated hydraulic field materials that are contractive, or hydraulic field materials that are lightly dilatant. And also, in that case, this is just for some of the locations. And then here you have more specific units like the Merritt sand that I was talking about before, and also the Pleistocene Bay mat and the Pleistocene, another unit of the Pleistocene Bay mat. So something else we had was the ground motion recording. And from the ground motion recording, we were able to inspect on when liquefaction was happening. And liquefaction usually occurs when you have, not sure if you see the frequency content here, it is changing dramatically here. It's these waves that were happening very often, to say it in a way, now they are lagged in time, and they are going to be happening, less frequently. So that's associated with liquefaction. And we, this is the acceleration. We transform the acceleration into the cyclic stress ratio. And based on the cyclic stress ratio, we estimated, what is our demand. And then based on the cavity expansion simulations that we conducted and the CPTs, we estimated what is, our state parameter. And in that case, we actually, for the two units we considered, we had, liquefaction in one case, and we had no liquefaction in another case. So, and that's just a way on how to, combine the information of mechanistic parameters to assess liquefaction. So in terms of closing remarks over here, first of all, I want to highlight again that there are contrasting procedures that are used in the assessment of static and cyclic liquefaction these days. And there, in my view, there is not really a need to have that contrast. I think we should be using as much as possible mechanics to inform our assessments. And that's kind of my view. Then, a critical state soil mechanics-based framework that is addressing the limitations of semi-empirical procedures for assessing cyclic liquefaction has been discussed. And in terms of limitations, I'm mainly referring to the fact that when you have an empirical-based calibrated procedure, it's going to be working fine for, for your data. Nothing is assuring that that's going to be working fine outside your data. The framework, that we proposed was assessed using a large CPTU database. That was the New Zealand database that is having, I believe from the top of my head, we were having like 5,000 CPTs or something like that. And then we use all of that with machine learning concepts to really rank and assess different options to assess liquefaction manifestation. So in particular, the performance of the CPTU-based inversion procedure was assessed, and we provided recommendations into updating the cavity expansion-based procedures to do that. And that's one of the key contributions of the paper. And last, I just illustrated the application of the framework to a case history on the Loma Prieta earthquake. So with that, I'm closing the presentation, and I'm more than happy to receive questions as needed. And thank you very much for listening.
Thank you so much, Dr. Macedo, for your brilliant presentation. So far, we haven't received any questions. So if you don't mind, I'd like to start with one of my own.
Sure.
Again, as I mentioned, an outstanding presentation. Thank you very much for bringing this topic to the Brazilian geotechnical community. I thought it was extremely interesting the way you've used machine learning to distinct the variables you were dealing with. You mentioned the receiving operating characteristic technique. I wonder if you've tried any other algorithms, and what was your main deciding factors for using this algorithm in particular?
No, it is, yes, I would say a useful technique. When you have a classification method, it's just a useful technique to rank different, procedures. There are other techniques that could be used as well, but it's not really, our focus was not really trying to push different data-driven techniques, but trying to really make the case that the knowledge that we use for static liquefaction assessments can be also used into cyclic liquefaction assessments. Because right now, for example, if we look into the forensic studies after Fundao failure, after Brumadinho failure, those reports are relying heavily on critical state soil mechanics concepts and the parameters that I have described on this talk. However,
Exactly.
when engineers are assessing cyclic liquefaction, it's mainly empirical. So we are not taking as much advantage of everything else that we have learned from the static liquefaction. So the idea was that the classification could be, the machine learning part could be different things. It's just, machine learning, even though we use it a lot, but it's just a technique at the end of the day that is just helping us for the assessment. But it's not really what we would call the core of the things, at least on those assessments.
I see. Thank you very much. I'm gonna try to quickly translate this question.
Sure.
Pessoal, por enquanto a gente não tem nenhuma pergunta no chat, então eu aproveitei para fazer uma pergunta eu mesmo, uma dúvida. O professor Macedo mencionou os algoritmos de aprendizado de máquina, de machine learning que foram aplicados na pesquisa. E, em particular, ele citou um algoritmo. Eu perguntei para ele por que foi escolhido esse algoritmo, se eles tentaram alguns outros e tal. Ele me trouxe um retorno que o objetivo principal da pesquisa é de tentar fechar um pouco esse ato entre as análises estáticas e cíclicas de manifestação de liquefação. Então, o objetivo foi de introduzir aqueles dados empíricos das análises estáticas para as análises cíclicas através de um algoritmo de machine learning. E poderiam ser utilizados outros e tal, mas não era o principal objetivo. Então, era como se fosse uma parte secundária da pesquisa. Bom, pessoal, eu acho que a gente não tem nenhuma pergunta. Se o professor estiver de acordo, acho que a gente pode encerrar. Professor, we don't have any questions so far. So if you agree, I think we can start for now.
Sure. Yeah. No. Thanks again for the invitation. Thanks for listening. And you can, if you have questions, send them to Felipe or Diego, I guess. And everything I've had to talk about is on the papers that we have published, so you can also refer to them.
Okay.
Yeah.
Thank you so much. Obrigado, pessoal. Obrigado novamente, Geotecnia Brasil. Como o professor disse, se tiverem alguma dúvida, podem ficar à vontade para entrar em contato com o Felipe Cruz ou comigo também, que a gente pode direcionar as perguntas ao professor Macedo. É isso. Uma boa noite a todos. Espero que tenham gostado.
Bye. Take care.